In this video, we're going to go through Chapter 7 of the chemistry textbook. Chapter 7 is on quantum theory and the electronic structure of atoms. Specifically, we're only going to go through the quantum theory portion in this video. In the next video, we'll go through the electronic structure of atoms portion. Now, I did make a separate video that goes into quantum theory in more depth. It's about an hour and a half, hour and 50-minute long video. There's also another video that talks about what is electromagnetic radiation. That's kind of tied into how quantum theory was developed. And so I would encourage you to watch those two videos. This video, we're going to flip through the textbook and do a more condensed version of the longer quantum theory and electromagnetic radiation video. You don't need to take a full course in quantum mechanics to be able to understand anything in this course, to be able to understand general chemistry. But because quantum physics is prevalent at the atomic scale, it's technically present in all circumstances. I mean, it's a fabric of the universe, but it really manifests itself. It becomes more prevalent, at least to human perception, at the atomic scale. At normal scales, at human-sized scales, everything to us we observe as obeying Newtonian mechanics. But again, because quantum physics is so prevalent at the atomic scale, and because in general chemistry we're dealing so intimately with atoms, molecules, electrons, protons, neutrons, it's good to have a basic understanding of quantum theory and how it was developed. And that's the purpose of the start of this chapter and what we're going to go through in this video. All right, so quantum theory. What is quantum theory? How did it develop? Well, in the 1800s, throughout the 1800s into the early 1900s, a lot of studies were being done on radiation or light. And at the same time, they were also studying the makeup of matter. So they were trying to understand the building blocks of matter. We've talked about this, trying to understand atoms. They in the late 1800s or the early 1900s, they discovered the electron and they discovered the nucleus. And so they were trying to understand all at the same time, what exactly is light? What is radiation? What is light? That it comes from the sun. What is that? It gets reflected off of surfaces. What is light? And what is matter made of? They accepted the theory of these building blocks of matter, but that was called atoms. But what are these? What are they made of? Okay, now when it comes to light, before the 1800s, the most accepted theory was of what light was Isaac Newton's theory, and basically he looked at light as a rays of light. So not really a particle, just more like a ray. And from our experience, this isn't a bad theory. I think you would agree. We observe rays of light like this. I mean, you can see it's like a light ray. But it's kind of confusing because light is kind of like a wave. I mean, it does seem to spread out like a wave. If you turn a light on in the kitchen and you go around a corner, the light it comes into the room and then it spreads out, and that's how it reaches you. But then it's spreading out, and at the same time, you do see these light rays as well. So it's confusing. But the prevailing theory is Isaac Newton's ray theory. But in the early 1800s, Thomas Young performed his experiment. It was a double-slit experiment that showed that light was a wave. Or at least to some degree, it had to be a wave. Because you shine light through a double slit, and you get a pattern, an interference pattern like this, which is something only waves do. Particles don't do this. But again, there's an experiment like this that shows light definitely behaves, at least in some sense, as a wave. But then it's not like Isaac Newton was crazy. I mean, all of his observations, the way he saw it, it seemed that light behaved like a ray, which is kind of like a particle. You know, a particle moves in a straight line like a ray does. Okay, so the chapter opens by talking about properties of waves. It just gives a basic overview of waves. Okay, but what you can imagine is the physicists, the scientists at the time, and they were professionals going full steam in their field. In general, they understood all of the physics at the time concerned with waves. And when I'm referring to waves, I'm not talking, a light wave. I'm talking about literal waves, like water waves in the ocean. Exactly what you would think about as a wave, that's what I'm talking about. In physics and science, you study the phenomena of the world around you. Any any phenomena in the world around you where there's waves around us. So people did studies on waves back in the early centuries before the 1800s. You could describe waves, the wavelength, the speed of the wave, the frequency of the waves, the height of the waves, the amplitude, how they spread out. Put math to that. If you send a wave like a water wave through a double slit, it's going to make an interference pattern like this. At least in the sense that if you observe the height of the water waves, a certain distance from the double slit, you'd have higher waves here and then waves that cancel each other out, so no amplitude here. Higher wave here, no amplitude here. Thinking about like a water wave. That's what waves do. That's how waves behave. And so in the 1800s, waves had already been studied a good bit, just general waves. So the physicists, they were masters in all of physics, all areas of physics. They understood waves, wave behavior. Okay, so now it talks about just in general, what is electromagnetic radiation? I've got a full video on this. Electromagnetic waves it's a propagating electric and magnetic field. The electric and magnetic fields are reinforcing each other, so it doesn't damp out. It doesn't damp. It just goes through space until it interacts with something. Then it gets absorbed by that something. These come from accelerating electrons. When electrons or any accelerating charge, but we think about accelerating electrons because that's, in nature, it's really the electrons that are in constant motion around the relatively still nucleus. So, but these electrons, when they jump from orbital to orbital around the nucleus, they give off electromagnetic waves. But it's not just electrons around the nucleus. It's any accelerating electron. So in an X-ray gun, X-rays are generated by abruptly stopping high-speed electron currents. So they decelerate so fast, they give off high-energy X-rays. But we call this a wave. The main reason why this is called an electromagnetic wave is because of this. Here is a propagating electric field, and then the perpendicular magnetic field, and it's in a wave like this. This wave has a certain frequency, a wavelength, a speed, the speed of light. So regardless of whether you're looking at light as a ray, like a ray of light, or even the double slit experiment wave properties, in general, you're still thinking about it as an electromagnetic wave in this sense. This wave property, the wave property of the electric and magnetic field. Okay, now, so radiation was being studied, and one area of radiation that was trying to be understood was the black body emission spectrum. And I'm not going to get into details of this. Check out the electromagnetic radiation video if you feel like you're too confused. But so you have intensity of radiation and frequency of the radiation. Frequency meaning the frequency of the cycles per second of the propagating electric and magnetic field. And all black bodies have the same emission curve, something like this. It's only dependent on the temperature of the body. You change the temperature, this curve changes, but that's it. It doesn't matter the material, the state, solid, liquid, or gas. It doesn't matter. It's just the temperature that dictates the emission curve, the black body emission curve. And they were trying to come up with a formula to model this, but they were having trouble. No one could figure out how to model it. The models would predict the curve correctly for low frequencies, but then break down at higher frequencies, and vice versa. Well, Max Planck came up with an idea that allowed him to successfully come up with a formula to model this emission curve at different temperatures. And just an FYI, you can imagine you can't just come up with some completely arbitrary formula. Like you're going to make a piecewise function that has 8 different pieces to model the whole curve at different frequencies. Because you have to at least to some degree explain your equation, right? So again, you could I'm going to model the curve with 10 different pieces of a piecewise function, or a piecewise function with 10 different pieces. Well, no one's going to buy that, and for good reason. That doesn't. How are you explaining that? So, but what Max Planck said was that he theorized that the energy of the electromagnetic radiation that's emitted from a body, that energy is what's called quantized. It can only have specific, unique values. It can't have just randomly any value. So in other words, you can think of it like if I have, this is a formula for energy and I have some function of whatever, a function of x. But then I say it's times n, where n is an integer from 1 to infinity. Well, I can only use n is equal to 1, 2, 3, 4. So this energy is quantized. Whereas if I didn't have the n, I could hypothetically put in for x as any real number, or not even any real number. Even there's an infinite number of values from even 0 to 1. Technically, like from between 0 and 1, there's an infinite number of values. So if you've got a continuous variable, it's not quantized. There's an infinite number of values. But if you put an n here, then it can only take on specific values. That's the idea. That's what Max Planck said about the energy of the electromagnetic radiation that's emitted from the black body. And so what he said was that the energy of some electromagnetic radiation emitted from a body is equal to this constant h times the frequency of the radiation. So this chart here you can think of it like energy frequency, or it might be intensity, but in energy intensity and just energy is one and the same thing, at least for the purposes of this discussion. But as a function of frequency, right? So you've got this curve. And so if you assume that the energy of any electromagnetic radiation being emitted is equal to some constant times the frequency, then his formula that he could come up with a curve fit for this that worked at all temperatures, right? This curve changes depending on the temperature. This is temperature 1, temperature 2, temperature 3. If he made this assumption, and just with this one constant value, this h, then he could make the curve fit work. I mean, and that's powerful. It's not like he's saying, I'm going to change up all the parameters for different temperatures, or we're going to have a piecewise function that goes from one part goes from here to here, one part goes from here to here, one part goes from here to here. No, this is pretty simple. It just, as long you use this one constant and assume that the energy of the electromagnetic radiation is quantized, and he came up with a curve fit that worked across the board. Okay, but still, it's still kind of out of the box. This quantized energy levels. That's not what we observe in nature. And so it's not like when he published his paper on this that it blew up immediately. It was interesting that it worked across the board with just this simple constant here, but still it's kind of strange. So it didn't take off, it didn't blow up immediately into the recognition it has today. But okay, this constant here though, this h is a famous constant, and it's at the foundation of all quantum mechanics concepts. This h is called Planck's constant. Okay, next they talk about the photoelectric effect, and I go into more detail on what the photoelectric effect means in the quantum theory video. But what they're talking about is it was like a few years after Planck published his paper, and they were trying to understand what's called the photoelectric effect, which is when current is given off, or electrons are given off or emitted from a metal surface when you shine electromagnetic radiation on it. And again, I go into all the details of this in the other video, but to answer a lot of the questions that they were having trouble answering, Einstein referenced Planck's quantized energy theory, this idea of this quantization theory. And so again, Planck said that the energy emitted, the energy of the electromagnetic radiation emitted could only have certain values. Einstein said that light, so that's electromagnetic radiation emitted from black bodies, but also just light in general. Light is made up of these individual packets that he called photons. And the energy of each individual photon is equal to that energy that HV, that Planck developed. And thinking about light in this way, and how exactly Einstein, what he laid out about what a photon is and how it behaves, I go through in the other video, but that helped answer all of the questions that they couldn't figure out when it came to the photoelectric effect. Okay, so this is interesting, but it's still a little bit confusing because, again, you have experiments like this where light is clearly behaving, at least to some degree, as a wave, but the ray theory is not that crazy. The ray is kind of close to that particle theory. It's not that crazy. Because look, we can see light rays. And then now Planck's quantum theory in combination with Einstein's photon theory, that makes sense as well, right? The photon theory it makes sense, and it's explaining phenomena precisely. Okay, so now with this photon and energy quantization theory, with the corresponding Planck's constant that ties it all together, Niels Bohr came up with a model that explained the emission spectra of the hydrogen atom. So they were studying radiation at the time. Black bodies emitted these continuous bands of radiation. So it was just kind of all radiation in general, you can think about. But if they took low pressure gas, so like a low number of gas molecules, they give an example here. So you have a low pressure gas inside a tube like this. They run a high voltage through it to heat it up. Because it's heated up, it's emitting electromagnetic radiation. They pass that emitted radiation through a prism so it can separate the different frequencies. What they found was that all types of gas had a unique emission spectrum. So like shown here in terms of frequencies. Here they're just showing visible light because initially the only radiation they were aware of was visible radiation. They had to discover that there was invisible radiation, so it was a process. But just looking at visible light here, the visible light spectrum, each type of gas, so mercury, helium, lithium, calcium, so even these non-metals, you can, if you heat it up enough, you can make a vapor, right? So even these non-solid, even elements that aren't solids at room temperature and pressure, but you can heat them up and they'll vaporize. Everyone has a unique emission spectrum, and it's kind of like a fingerprint. You can look at an emission spectrum and then identify what element that spectrum comes from. And so in addition to, as Planck did, modeling the black body emission curve, another project challenge you could work on was modeling or explaining emission spectrum. And they started with the hydrogen emission spectrum. That was the most basic, or the first element in the periodic table. So again, with the idea of energy quantization, the idea of the photon and Planck's constant tying it all together, Niels Bohr came up with a model for the emission spectrum of the hydrogen atom. And all this model was saying was, it was thinking about electrons in atoms as only being able to occupy certain orbits. They were still kind of thinking about electrons as orbiting the nucleus in the same way planets orbit the sun. There was a transition. They had to transition from that theory to a different theory that we're going to get to in a second. So the hydrogen atom has one electron, just one electron, and the electron can only occupy certain orbitals, specific orbitals, based on that they're quantized. So like those orbitals have certain energy levels, right? That's the idea. They're predicting the emission spectrum of the emission spectrum of the hydrogen atom, the different frequencies, which corresponds to energy. The lower the frequency of the radiation, since the speed of light is constant, the lower the frequency, or no, the lower the wavelength. The higher the frequency, the higher the energy, because the speed is the same. So if you have a higher frequency but the speed is the same, the energy is higher. So to predict that emission spectrum of hydrogen, the hydrogen atom, the different frequencies of light coming from the hydrogen atom when it's heated up, Bohr came up with a formula that predicted these energy levels, and he came up with the theory that when the electron jumps from one orbital to another, that's when it gives off a photon. So here we got this delta E here. Delta E is equal to H. It's always equal to HV. And it's dependent on jumping from one orbital to another. And this predicted the hydrogen emission spectrum. It worked. And also there was questions about, well, how, if electrons are orbiting the nucleus, then they should be constantly giving off energy, and then they should get the orbit should get smaller and smaller and smaller until the electron annihilates itself in the nucleus. But this orbital theory, this energy quantization theory, the idea was that the electron could only occupy certain states. So it couldn't just go into the nucleus like that. And this was explained by that there's a ground state, or the ground level, which refers to the lowest energy state of a system. And so that was the idea. You had this ground state and excited states in which the electron was at a higher energy than the ground state, but you couldn't once the electron's at the ground state, it can't go any further than that. That's the most stable state. So it's not just going to keep spiraling into the nucleus, giving off energy. So this was groundbreaking and interesting, and the theory worked to predict the emission spectrum of the hydrogen atom, and it gave a sense of the physical reality of what was taking place in the atom. But this method didn't work for multi-electron atoms. And then furthermore, it also didn't explain the why. So if you think about it, you're predicting the emission spectrum of the hydrogen atom, and that's fine, but where do these orbitals come from? Why are they quantized like that? How do you predict the shape of the orbital? I mean, yeah, you can use the energy level to get a sense for the shape, because you know, like accelerate, or v squared over r is equal to the acceleration, but you're not explaining where the experimental data is coming from at all. And so the next step was when Louis de Broglie theorized that since light is clearly exhibiting both wave and particle behavior, then that must be what everything in nature is doing, even matter, right? Because when you think of matter, that's when you think of a particle. Yes, like a water wave is made up of matter, but you can think of the wave as propagating through the matter. The water wave particles, the H2O particles, aren't waves. The wave is moving through it's not a mass, right? The wave is not mass. An electromagnetic wave doesn't need a medium to propagate through. It can propagate through empty space, but it's still not mass. You don't think of it as it's not a particle, right? We have the photon idea, but it's not mass, is it? Well, it looks like it's exhibiting these particle and wave-like behaviors. So de Broglie theorized, well, then that must be what matter is doing as well. And de Broglie came up with a formula that is based on Planck's constant. So again, Planck's constant is at the foundation of all of quantum mechanics. And it said that, so if you have any mass, even like a human being, any mass, if you take Planck's constant divided by that mass times the velocity of that mass, then that's equal to the wavelength of that mass. So it's suggesting any moving mass has a wavelength. Now, if you experiment with this formula, you'll see that any mass that has size on a macro scale, so like a human size scale, the wavelength is way too small for us to even to perceive. Again, I think I mentioned this, but maybe in thousands of years, we'll be able to actually tap into wavelengths of objects on our size scale. But at least as far as now, it means nothing to us, these wavelengths. Even like a particle of dust, that's way too big to have any meaning, its wavelength. The wavelength of mass comes into play at the atomic scale and the subatomic scale. Okay, so now with this in mind, de Broglie, you can imagine he said, okay, well, since mass has a wavelength, since we're thinking about now that mass has a wavelength, any moving mass has a wavelength, then the orbiting electron in a hydrogen atom or any atom also has a wavelength. And with that in mind, you can think about he went to his physics textbook and reviewed all of the existing knowledge on waves, just regular waves, traveling waves, all kinds of waves. One kind of wave is a standing wave. That's a special kind of wave. So it's a wave that if you have something like a string or anything it's fixed at the ends, then the wave just bounces back and forth off the ends, and like shown here. And it's only for certain wavelengths. So you can imagine, depending on how you excite the string, you'll have different wavelengths. There's only certain wavelengths where you get a standing wave like this, where you get this, it looks, if you look at Google standing wave, it looks just like this. It's like these loops that are standing in space. But for all other wavelengths, it's like a jumble of nothing. And so what I imagine is de Broglie was going through his physics book, looking for something interesting that he could work with, and he saw. So if you go to your physics textbook and you look at the formula for standing waves, it has an n in it, like an n for an integer. It's only It's certain integer numbers of wavelengths, like 1 wavelength, 2 wavelengths, 3 like it's integers like that, which is, I'm sure he saw that and said, well, look, that's the same formulas they're using in the hydrogen emission spectrum. They have this N in it, this quantized N in it. To me, I imagine he thought, well, that must have a tie. And he put it together. And what he said was that so the basic idea of a standing wave is like a linear, here it's not a string, it's just like a compartment, but the wave bounces off the walls. But it's a line here, but you can take a line, any line that has a certain, like has a length, and say that if you think about a circle, 2 pi r is equal to that length. So you're wrapping this line around a circle, right? If you say 2 pi r is equal to the length of the line you have, then you've wrapped that line around a circle. And so all he said was that these quantized orbitals, they're based on the radius of a circle that results in a standing wave. It's something like this: 2 pi r is equal to n lambda, where n is an integer. So it has to be 2 pi r has to be equal to a whole number multiple of the wavelength of the standing wave, right? If the radius was in between those values, this was a jumble of nothing, but it was only at these certain radiuses where you get this clear standing wave. And again, where is this coming from? It's because you're assuming that the electron has a wavelength. That's the idea. It's this wave-particle duality. The electron as mass has a wavelength based on this formula. And so using this formula, using a formula like this, and using the energy levels that Bohr developed, de Broglie was able to provide a answer to that why question for the emission spectrum of hydrogen, provide a physical basis for it. However, the de Broglie method didn't work for other atoms, multi-electron atoms, only the hydrogen atom. Okay, so what happened next? Well, even though this de Broglie method didn't work for all atoms, it was groundbreaking. It was this theory that, I'm not sure if I'm getting all the history exactly right, but the way I imagine it is, there were 2 groundbreaking things that de Broglie did. One was, this wave-particle duality, like the electron could have a wavelength, but then also this idea of then going to existing knowledge about waves, like in the physics textbook you can think about, and tying that in to the behavior of the electron, this method, this idea. And so what you can think about is, after this, to try and solve this problem for the multi-electron atom, other scientists began looking through all the existing knowledge in the physics textbooks about waves and try to find some connection. So maybe forget about the standing wave, let's look at other waves and try and find a connection. And what I imagine is, I'm not giving this isn't a history video. What I imagine is somebody thought about the double slit experiment that conducted with light. So, well, first of all, whenever, I forgot to mention this, but whenever de Broglie came out with this theory, before this theory, there had already been double slit experiments conducted with light, because there was already that existing wave-particle duality question that came when it came to light, like we talked about earlier in the video. And so you can imagine it wasn't that easy to do an experiment like this, because you have to pass, what they were doing is they were passing one tiny amount of light through the double slit at a time. They would shine it at the double slit, just a tiny amount, just a speck of light, which would, you would think about could probably be like a photon, which seemingly would be a photon. It looks like a photon, right? It's like a dot. Looks like a particle. Just one at a time. They already knew based on the Thomas Young experiment, if they passed just a full beam of light through at a time, they would get interference patterns like this. That's what we talked about here. This is in general what happens when you pass a full beam of light through a double slit. But with the photon theory, you can imagine they're thinking, well, what if we try and pass one photon through at a time? Just a tiny speck at a time. And this isn't that, you need technology to do this. This isn't that easy. So they did this one at a time. Pass one through, it hits the screen, stop. Wait 30 seconds. Pass another one through. It hits the screen here. Stop. Wait 30 seconds. Pass another one through. Hits the screen right here. Stop. Wait 30 seconds. Keep doing that. Let it build up. It still builds up to this. So that's even more confusing, right? It's like the photons, when they pass through alone by themselves, they're still interfering with themselves. So again, de Broglie, looking at this evidence for this wave-particle duality of light, theorized that also matter had wave-particle properties. And when he came out with this theory, they also tested, they said, let's try this experiment with electrons, the double slit experiment with electrons. So shoot one electron at the double slit at a time. Same result. This is the electrons develop an interference pattern. Okay, so now back to trying to solve the multi-electron atom model. What you can imagine is someone took a look at this experiment with photons, not electrons, photons. And they said, well, this is interesting because this is here we have a direct tie between photon behavior, so like particle behavior, and wave behavior. So like with the electron, you could say, well, we have that same tie, but not really, because this is only based on de Broglie's theory that he kind of made up, right? The fact that electrons are waves as well. Here, we know that light is a wave. I mean, light has certain frequencies coming in. Like it's different than the electron. It's not, we got much more evidence, physical evidence, that light is literally a wave. We're not really just theorizing that light is a wave. We see it. We have evidence of that. Again, like light, they could measure frequencies of light, wavelengths of light. So, and we go through this in more detail in that video, the quantum theory, development of quantum theory video. I'll post a link to that video and the electromagnetic radiation video in the description. But so what they said was that let's use our knowledge of waves. So like waves passing through a double slit, like they had already studied if you pass a water wave through a double slit, how the water wave comes out and how it interferes, and they had formulas for that. And unlike the electron, when it comes to shining light, they know the frequency of light coming in. The light has a literal frequency, a wavelength. So they said, let's use we know how actual waves, water waves, even light waves, behave when they pass through a double slit. Let's use all of those formulas, kind of like de Broglie did with the standing wave. Let's use the formulas we know about traveling waves going through a double slit, and the information we have here about the particles, right? We can see like the particles hitting the screen. We have experimental information here to make a tie between wave and particle behavior, a mathematical tie. And even with that mathematical tie, you can analyze that formula you come up with and explain the physical phenomena as well. Okay, so just to make this clear on what they're doing, what they're trying to do here, it's kind of like a position function. When you think about Newtonian mechanics, classical mechanics at the human size scale, for how they model roller coasters and baseballs, you get the position of something with respect to time. That's what they're trying to do. They're trying to get the position of an electron with respect to time, specifically around atoms. That's what they want. Once you have a position function, you can take a derivative of that, get a velocity function, take another derivative, get an acceleration function. With the position function, you can also know what the shape of the path of the electron is, so you can get the shape of the orbital. That's what they're trying to do. They want to get a position function for the electron. So ideally, they would want to be able to predict that when they shoot an electron at the double slit, they want to predict where it's going to hit. That's what we do in classical mechanics. If we know with certain boundary conditions, so if the baseball was hit with this force at this direction, we can predict where the ball is going to be at any point in time. That's what you want to do. You want to be able to predict, I guess the voltage that you sent the electron through at. You know the direction that you sent the electron through at the double slit. You know where the double slit is in relation to the electron gun. So based on those boundary conditions, you can predict the electron's going to hit here. Then the next electron's going to hit here. That's the idea. And that's kind of what we do with water wave functions. You can predict the height of the water wave at a certain point in time. Like you also have like a position function in classical mechanics. You have position functions for water waves. If you know the boundary conditions, so how, what excited the water, what force started the wave, and what was the direction of the force, then you can predict, it's not like a particle, but you can predict, okay, at this moment in time, this peak is going to be here, this valley is going to be here, the speed of the water wave is going to be this. So that's a wave function. You have position functions of particles in classical mechanics, and you have wave functions as well, where you can predict, you can model the whole water wave or the whole sound wave based on the boundary conditions that you input. Okay, now the only thing is, what they realize is that the best they can do is give a probability of where the electron is going to hit. That's the best they can do. So again, they're trying to tie the incoming wave equation. They know the wave properties of the light. They know the double slit interference properties of something that goes through a wave that goes through a double slit, and then bringing that in combination with the position that these dots strike the screen. The best they can do is relate those two with a probability of where the dot is going to hit, not the exact position. And it was from this kind of analysis where the wave equation was invented. When you hear wave equation in the context of quantum mechanics, wave equation, it's like a position function for a particle, any particle, even a human being. But it only really manifests itself, as far as we can perceive it, at atomic and subatomic size scales. But if you're it's a position function trying to predict the position as a function of time of like an electron, for example. Or, it could be anything that's small enough size, even a proton. That position function is giving the probability of finding that particle at that position at that time. That's the idea of a wave equation, and it's called a wave equation because it's based on the foundation of it is wave properties. You can see this when we go in the full video, but it's founded on wave properties, just like the standing wave. The electron position here was with the foundation of it was the standing wave. The wave equation is the same way. Okay, now you might be thinking, well, the electron has to be somewhere, and this is the best we can do to predict its position. But, in thousands of years, as technology increases, we'll eventually get an actual equation that could tell you exactly where the electron is. You also might be thinking, how could an electron, how could a particle be interfering with itself? How could a photon shot by itself be interfering with itself? A photon or an electron, that's what it seems to be doing. Like, how could this be happening if you're just shooting it one at a time? Well, the Heisenberg uncertainty principle helped to answer some of these questions. So again, here it's based on Planck's constant, and this principle, it's just making a statement on how, if you increase the certainty of the measurement of the position of something, so you get the most advanced instrument to measure position, you're going to have to be sacrificing accuracy or precision as far as measuring the momentum of that something. So even in thousands of years, if we get the best instruments, there's always going to be, we can only go so far. And this Heisenberg uncertainty principle is also used as a reference to try and wrap your people's minds around the idea of the electron or the photon interfering with itself, being in multiple places at once. But quantum mechanics is still, it's open-ended at the moment. It's not, there's a lot of argument going on. There's a lot of different theories. You can still think that, okay, yeah, you can't measure the momentum and position, together with a full level of accuracy. Okay, but that's, to me, you could say, well, that still means that the electron is somewhere. We can just, as observers, we'll never be able to know exactly where it is. But it still means that it's somewhere, right? So if that's the case, then why is it interfering with itself? To be interfering with itself, it's almost like it has to be in two places at once. So you can think about that for yourself. But that's the Heisenberg uncertainty principle. It just helped to answer some of these more, I guess you could say, like trippy questions about what was taking place with these experiments that were just, mind-blowing. Okay, now this wave equation that we talked about here, this is like a one-dimensional situation. So you can look at this, you can see that this is not a function of, everything's constant in the height direction. And it's also, there's like a symmetry in the left to right direction as well. Well, with the multi-electron atoms, and just even in general, you need a 3D equation that, potentially everything varies in all dimensions, in all three dimensions, right? There's no in general, there's no symmetry like this. If you're trying to predict the position of a particle, like an electron, with respect to time. So the next big challenge was extending this idea to 3D, this wave equation idea to 3D, and then using it to predict the electron structure of multi-electron atoms. So you got to extend it to 3D and then also apply that extension to successfully apply it to predict the emission spectrum of multi-electron atoms, right? You come up with you solve the wave equation that predicts the positions of the electrons successfully based on what was developed with the wave equation. And at the same time, you can also use that emission spectrum jumping orbital idea to predict the emission spectrum of all of the multi-electron atoms. Okay, so Erwin Schrödinger solved this issue. So Schrödinger didn't invent the wave function. It's called a wave function, not a wave equation, the wave function. So it's wave functions. Wave functions, a general wave function predicts the position of, or the position of a particle like an electron with respect to time in general. A general wave function has nothing to do with atoms, electrons around atoms. You can do a wave function on anything, on a person. You could do it on anything. Schrödinger didn't invent the idea of the wave function, but he came up with a way to solve a wave function for general 3D, as well as to use what he had come up with to predict the electronic structure of atoms, multi-electron atoms. Okay, and so they call this the Schrödinger equation. It's that full 3D equation. And basically what the equation is doing is it allows the velocity of the particle, like the electron, to change. But if you think about, like, if you're modeling an electron, just think about how the mass is constant, but the velocity can change, obviously, and the acceleration. But no matter what, the particle always has the de Broglie wavelength. That's the idea. That's the way that it's a differential equation. That's the way it's set up. The particle, you could have the non-constant mass, but thinking about the electron, let's think about the electron. The electron mass is constant. Obviously, the velocity can change, the acceleration can change, then the position obviously can change. But it's set up to where no matter what, that particle always has the de Broglie wavelength, that's the foundation of that is Planck's constant. Okay, now to apply the Schrödinger equation, the 3D wave function, to a specific case of electrons around an atom, you have to apply, or to any case. To apply to any specific case, you apply boundary conditions based on that case. The boundary conditions that are applied to an electron, any electron, even in a multi-electron atom, are orbiting around an atom. Not orbiting anymore. It's not really, you don't think about it as orbiting like a planet, but those boundary conditions are the quantum numbers. You have three dimensions, you need three boundary conditions. That's what the quantum numbers are about, right? The principal quantum number, the angular momentum quantum number, the magnetic quantum number. There is a fourth quantum number, but the electron spin quantum number, that has nothing to do with the Schrödinger equation. This is independent. It's those three quantum numbers, the first three quantum numbers. That's what describes the orbital shape, the position of the electron, the energy. The first three quantum numbers, that's where the electron configuration comes from. The fourth just talks about the spin of the electron. That's a different subject. Okay, and also one thing to note is that what they do is they solve the Schrödinger equation for each individual electron, right? Each individual electron has its own wave function. That's what you're doing. You're saying, okay, we have this electron. What's its wave function? Well, let's solve its wave function so we can get its position with respect to time, or at least the probability of its position with respect to time. Then we can take that derivative and get its velocity, and then With its velocity, we can get its energy level, and then we know the energy level of different quantum states, and we can imagine the electron jumping from one state to another, and we can make sure that predicts the emission spectrums correctly, and it did. And you might be wondering, well, how did they account for the interactions between different electrons in multi-electron atoms? It's pretty simple. It's more simple than you think, and I talk about that in the full-length video. Okay, so that's a summary of quantum theory, and that gives you a sense of where the quantum numbers come from. In the next video, we're going to go through the meaning of these quantum numbers and talk about the actual electron configuration.